This is the Pencast for section 8.1, Linear Systems. In this section, we're going to be defining what is meant by a linear system of differential equations, and we will see how we can use matrix notation to make the problem of writing these systems a little less cumbersome. So basically we'll use some good notation. Now we've already seen some systems, so the idea of a system should be somewhat familiar here. And what I will point out, and I'll mention again a little bit later, some of the theory here is going to look very similar to the theory that we saw when we studied linear equations, just 1D systems. Okay, so we will say that a homogeneous linear system of ODEs is the following, and you might guess what it's going to look like. It is going to be, well, a system, so a whole bunch of linear homogeneous differential equations. So dx1 dt equals some linear differential equation in x1 through xn. dx2 dt is similar, and then down to dxn dt. And these coefficients, notice that since this is a linear system, that a priori those, or just in general, those coefficients can depend on time. For us, a lot of the systems we are going to solve are going to have constant coefficients. But for the definition to hold, those coefficient terms, the a sub ij terms, those can be dependent on time. So writing that system the way that I just had it, writing a system like this is fairly cumbersome, and what you might notice is I'm kind of writing the same thing in every line. I'm writing x1 times something plus x2 times something, etc., plus xn times something. And so I'm writing that in every line. The only thing that's changing is the coefficients on each of those terms. So if you have seen matrix multiplication before, then you might feel that something like matrices would be helpful here. If you haven't, pause the video now, go read about how to multiply a matrix in a vector, and come back to me. So let's let x of t be the vector x1 through xn, so a column vector, and let's let A be what we'll call the coefficient matrix. So it's the matrix created by taking all of those coefficient terms. Then we can write our system of differential equations as x prime, the vector x prime of t, equals a times the vector x. So that's shortcut notation, or what we call matrix notation, for that differential equation, or that system of differential equations. And here we'll call x, that's my solution vector. So I'm trying to solve for this solution vector. So matrix notation, it's a convenient way to express this system of differential equations. And what I'd like you to do, especially if you're new to multiplying matrices and vectors, is check that if you multiply a times the vector x, you do indeed get the right-hand side of the system that I showed on the first slide. Okay, so let's see an example of how we can translate a system into matrix notation. So I have dx1 dt is 7x1 plus 10x2, and dx2 dt is negative 11x1 minus x2. In matrix notation, x prime, the vector x prime, equals the matrix A times x. Then this is going to be x, my vector x, is x1 and x2, so that those are its two components. And my coefficient matrix is just the matrix of coefficients, so 7, 10, negative 11, negative 1. So writing this in matrix notation, writing this in matrix notation would just be, just as I have indicated here, x bar prime equals ax, where that is x and that is a. What I would like you to do is read in section 8.1 about the existence and uniqueness of solutions to initial value problems when we have a linear system, read about fundamental sets of solutions, etc. What you will find is that the theory looks very similar to what we saw in the linear case. So take a read through that. We're not going to spend a ton of time on it, but it's important to see that indeed we have the same sorts of existence and uniqueness theory for linear systems of differential equations. So let's get a little example of how we might actually work with these sorts of solution vectors. So I'd like you to verify that the vector 1, 2 times e to the minus 5t solves the system I have written. dx dt equals 3x minus 4y, and dy dt equals 4x minus 7y. So in matrix notation, my solution vector x is the vector e to the negative 5t to e to the negative 5t. So the way I had written that factoring out, quote unquote, the e to the negative 5t, in vector notation, what that means is I want to multiply both components of my vector by that e to the negative 5t. So just so you know, if you haven't seen that before. So what we want to show is we want to show that this vector, e to the negative 5t to e to the negative 5t, solves the differential equation or the system of differential equations given by x prime equals the matrix 3, negative 4, 4, negative 7 times x. That's what we're going to try to check here. So if my vector x is e to the negative 5t to e to the negative 5t, then I differentiate, and when I differentiate, I just differentiate each piece individually. So x prime is negative 5 e to the negative 5t, negative 10 e to the negative 5t. So that's the left-hand side. So now what do I want to check? I want to check that a times the supposed solution vector equals what I just found for x prime. So I'll take a, which is 3, negative 4, 4, negative 7, times e to the negative 5t to e to the negative 5t. And when we multiply, we get, in the first component, we get 3 times e to the negative 5t minus 4 times 2 e to the negative 5t. And then in my second row, I get 4 times e to the negative 5t minus 7 times 2 e to the negative 5t. And if you do a little algebra, you see that we get negative 5 e to the negative 5t and negative 10 e to the negative 5t. Hey, those two things are equal. So my conclusion is that indeed the vector x solves my system of differential equations.